Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're back for lecture 6 of week 1. And in this particular lecture, we're going to discuss the most general intermolecular force. It's referred to as the London dispersion force. I should say up front that even though I say molecule interacting with molecule, it could be atom interacting with atom. It just depends on the particular system of interest. So you have to always keep that in mind as you listen to these particular lectures. In terms of an overview, we're going to focus on the last item on this particular slide. This is how a nonpolar atom or molecule interacts with another nonpolar atom or molecule. And the way that interaction occurs is by fluctuating induced dipoles, and that's referred to in the literature as the London dispersion force. The motivation behind all of this discussion is it's important to keep this motivation in mind. Ultimately, we're trying to estimate the interaction force between a tip, which is approximated by a sphere, and a flat substrate, which could be insulating or charged, insulating or conducting. And since the tip and the substrate are both made up of atoms or molecules, we have to be able to estimate the interaction potential energy between these individual atoms and molecules. And in particular, we got to know how that interaction potential energy varies with position z. And then we have to integrate that interaction potential energy over the geometry of the tip and the substrate. So that's ultimately where this discussion is leading. What we're trying to do is we're trying to systematically uncover the z dependence of the possible interaction potential energies that may be relevant in this discussion. So we'll pick up with this calculation in week 2 of the course. What can we say about this London dispersion force? Well, it's the most general interaction that can occur between two nonpolar atoms or molecules. So what we imagine is we imagine a nonpolar atom or molecule located at one point in space, another atom or molecule located in this slide it's called molecule 2, that's located a distance z away from the first molecule. And the question is, how could those two molecules interact one with another if they have no dipole moment, no permanent dipole moment? And the answer is that quantum mechanically, the electron charge cloud, let's say in molecule 1, is represented by a complicated sum of all the electron wave functions that comprise that particular atom or molecule. And it's possible that some of these wave functions at a particular instant in time have maximum values where the charge in that particular wave function is localized in one region of the atom or molecule. And if that occurs, that region of the atom or molecule is going to be slightly negative charged for a short instant in time. That therefore implies that the other end of the atom or molecule is going to be positively charged for a certain instant in time. So there's this instantaneous dipole moment that can occur, and this instantaneous dipole moment can then polarize another nearby molecule, and in the way that's shown, and net interaction can occur, which is attractive, and which would lead to a net interaction force between these two nonpolar atoms or molecules. So this is really a quantum mechanical effect. It requires a very close time correlation between the fluctuating dipoles in one molecule with the fluctuating dipoles in the second. And what the approach we're going to take in this lecture is we're going to try to develop a very simple model, physical model that captures the essence of these fluctuating dipoles and tries to illustrate to you how this fluctuation in dipole moment can actually give rise to a net attractive interaction. And the way we're going to do that is we're going to model each atom or molecule by a spring system. And in particular, the spring system that's shown in the bottom part of this slide illustrates two springs separated one from another by a distance z. There's a mass associated with each spring that's fixed, it's held in place. There's a second mass associated with each spring system that's free to move. And the charges associated with each mass exactly cancel out. So the fixed mass in this case has a charge plus q. The mass that's free to move has a charge minus q. And you might expect that at some instant in time, the displacement of the spring is zero. So these two masses lie one on top of the other. And the net charge of this spring system would then be zero. But at some instant in time, it's possible that there could be a fluctuation. That instant in time is captured in this cartoon. And what you see here is that the spring is extended, the charges are separated. There's then an instantaneous dipole moment associated with the spring system on the left, and that instantaneous dipole moment can then induce and interact with a dipole moment in a second spring system that's located on the right. So we're going to characterize the springs by a spring constant K, and we're going to just calculate what the interaction potential energy is of these two systems. So to begin with, let's do the simple case. Let's pretend that the charges on each spring system are zero, so there's no coupling between the two spring systems. And when that's the case, each spring system is identical. The interaction potential energy of each spring system is then a 1/2 kz squared interaction potential energy. This is the standard harmonic oscillator problem that you probably have seen in your introductory physics classes. Except now the difference is that we're considering these oscillating masses in a quantum mechanical system. So we have to insert these interaction potential energies into Schrödinger's equation. We have to solve for the energy eigenvalues of the Schrödinger equation in order to calculate what the total energy of these two uncoupled springs are. So that's done in the middle part of the slide. We write down Schrödinger's equation for each spring system. The coordinates for each spring system are different. So we've got Z1 and Z2. We've got an equation for both spring systems. The energy eigenvalues, E1 and E2, are indicated in Schrödinger's equation. This is a well-known problem in introductory quantum mechanics. And the answer to the energy eigenvalues that result from solving that particular differential equation, the answer is given in the bottom equation here. It just says that the energy eigenvalues, in other words, the allowed energies for the springs as they oscillate back and forth, is just an integer n plus 1/2 times the quantity h bar omega naught, where omega naught is the square root of k over m. That's the resonant frequency of that individual spring system. So n is a quantum number. It assumes an integer value. And because the two springs are uncoupled, you've got an equivalent equation for the second energy eigenvalue E2, and I indicate that by another quantum number n prime, where n prime is an integer that comes out of the problem. So the situation changes dramatically when the masses are allowed to have charge associated with them. In this case now, there's an interaction, an electrostatic interaction potential energy between the spring system on the left and the spring system on the right. And you have to sit down and we have to carefully work out what the interaction potential energy is for the coupled spring system. I write down the answer in the first equation here. I think if you follow through, you'll be able to write that down by inspection. It's pretty simple. The more complicated problem is to insert that interaction potential energy back into Schrödinger's equation and solve for the energy eigenvalues that are allowed when the two springs are coupled by U electrostatic, as I've got drawn. That's a more extensive calculation, and it's worked out in the appendix of this lecture. So for those of you that are interested in the mathematical details, you can refer back to that derivation. For those of you that are more interested in the final answer, I list that answer in the middle of this slide. And it turns out that when the two springs are coupled to get one with respect to the other by this electrostatic coupling, it turns out that the electrostatic potential energy of the entire system is lowered by an amount that's indicated in the middle equation here. There are actually three important features of this equation that should be noted. The first is there's an overall negative sign. That means it's an attractive interaction. The second is there are two model-dependent parameters. One model-dependent parameter is the charge Q squared over the spring constant K. And the second model-dependent parameter is this resonant frequency omega naught. That's the square root of K over M for the model system that we choose. In the appendix, I make the argument, I make the case that the parameter Q squared over K is roughly proportional to the polarizability that you might expect for that particular coupled spring system. So that parameter Q squared over K is now replaced by alpha naught squared in the last equation here. And I also make the argument that H bar omega naught, the resonant frequency of the system, that's roughly equivalent to the ionization energy of let's say a molecule or an atom that those coupled springs are intended to represent. So with this identification of parameters, you can then write a final expression for the London potential energy that develops for this particular system. That equation is written on the bottom of this slide. And what you can see is that the interaction potential energy in this most general case, this is the case where there is no permanent dipole moment associated with the atoms or molecules that are interacting. But even in this particular case, the interaction potential energy varies as 1 over the separation distance to the 6th power. So it's that 1 over z to the 6th term that's critical, that's a critical result of this discussion. If you have, I just mentioned, if you have two dissimilar molecules with different ionization energies and different polarizations, then that formula that I wrote down can be generalized to the particular equation that's shown here on the top of this slide. And this is a standard result that you find in many of the references in the literature. The ionization energy is, of course, a quantum mechanical parameter. It characterizes how much energy is required to remove an electron from the atom or molecule in question. And I just found a nice table of the ionization energies of the elements, and I reproduced that here on this slide just to give you a sense of the range of values of ionization energies that you might come into contact or that you might find if you're trying to evaluate this expression for different atoms that interact one with respect to another. I also wanted to mention that this is a simplistic model calculation that gives you some insight into the physics of what's going on. There's considerable effort made in the literature for these electronic structure calculations. These are state-of-the-art calculations, and I just reproduce results for two calculations for the case of an argon atom interacting with an argon atom, or a krypton atom interacting with a krypton atom. In these cases, the electronic structure calculation has to take into account all the electrons that surround the nucleus of the argon and the krypton atom. And as you can see, different computer codes which handle these electron-electron interactions in different ways give slightly different results. So there's not a well-defined answer. I believe the solid red curve in each plot is considered the gold standard result. That's the result that I think most people would agree is most correct at this point in time. So if you're more interested in this, I give you a reference that you can actually read, and it's a nice review article of these electronic structure calculations for different materials. I also wanted to mention that, this is a question I'm often asked, students will say, well, this model stuff that you've been doing is interesting, but it always involves molecular or atomic parameters. And what we're really interested in is we're really interested in the interaction of two solids, a solid tip with a solid substrate. Is there any formulation of this London equation, this London interaction potential energy? Is there any formulation that takes into account the fact that the two materials that are interacting are not atoms or molecules, but they're actually solids? And the answer to that question is yes. There's a very nice theory that's been developed by Lifshitz. And in the Lifshitz theory, the parameters of polarizability and ionization potential energy, those are replaced by dielectric properties of solids that develop when atoms all condense and form a periodic solid. And so the Lifshitz theory does not emphasize atomic or molecular parameters. It more emphasizes the dielectric properties of the solids that interact. And we'll discuss that Lifshitz theory in a little bit more detail in week 2 of this course. So if you stay tuned, we'll run through a quick discussion of the advantages the Lifshitz theory might offer. I'm often asked why this force, this London force, is referred to as a dispersion force. And the answer to that question is simple. In physics, any quantity that varies with frequency is said to be dispersed with frequency. So the word dispersion is associated with this concept that things depend on frequencies. Since these dipole moments that are induced have to be time correlated one with respect to another, their frequencies have to match up reasonably close in order for these interactions to occur. That's the sense of the word. That's the sense of the use of the word dispersion to describe the London forces, right? Of course, we've always calculated interaction potential energies. To calculate forces, we have to take a derivative with respect to the separation distance, and we have to multiply that derivative by -1. So that's always assumed in this discussion. It's pretty simple to take derivatives. It's much easier to calculate forces by taking a derivative than it is to sum up all the vector forces from the beginning. So that's the reason we focus more on the interaction potential energies rather than the interaction forces, although you can get the interaction forces in a very simple way from the interaction potential energies. I guess it's appropriate to sum up what we've discussed in the previous 2 lectures. What we've tried to work through is a systematic understanding of the interaction potential energies that occur when atoms or molecules interact one with respect to another by either dipole-dipole interactions between 2 polar molecules, by dipole-induced dipole interaction between a polar and a nonpolar molecule, and in this particular lecture, when both molecules are nonpolar, they have no permanent electric dipole moment. And the sum of these 3 interaction potential energies, they're referred to as the Keesom, the Debye, and the London interaction potential energies. The sum of those 3 are shown here on this slide. The important thing to recognize is that each interaction potential energy varies as 1 over z to the 6th power of the separation between the two things that are interacting. And there are characteristic features of each term that you should be able to recognize quite easily, right? The Keesom interaction is the result of a thermodynamic average. So KT appears explicitly in that equation for the interaction potential energy. The Debye interaction is related to the polarizability of one atom or molecule, so the polarizabilities of the atoms and molecules involved show up explicitly. And for the London dispersion force, which is an induced dipole quantum mechanical calculation, the polarizabilities show up explicitly, and the ionization energies, which are a quantum mechanical concept, right? Those show up explicitly in the final answer for the London dispersion forces. What all this means is that we're basically trying to calculate how two objects interact with one another, and in particular, we're interested in the z dependence of that interaction potential energy. And so, what this diagram is trying to remind you of is if you have two objects separated by a distance z, and if these two objects do not have a permanent charge associated with them, but if they have a dipole moment, or if their dipole moments can be induced, the net interaction between these two objects is attractive, means it's negative on this plot, and the way that interaction potential energy varies is 1 over the z to the 6th power of the separation between them. So that's indicated schematically in this slide by that dashed line. We're really interested just in the behavior of this interaction potential energy that's localized inside this gray box that I've indicated. Right? We're not so much worried about the repulsive interaction potential energies that occur when these two things get close together. That's more a point for discussion in week 2. And lastly, you can always get the force from the interaction potential energy by taking a derivative and multiplying by -1. So that's always assumed in this particular discussion. So this is ultimately what it means, right? We're just trying to understand how that interaction potential energy varies as separation between the two objects. I have a couple of tables here that just provide you with some numbers. These are tables that I found in the literature. I've referenced my sources in all cases, and it just gives you a sense of how big the Keesom, Debye, and London interaction forces are, one with respect to another, for a variety of simple atoms and molecules. In this particular slide, I draw your attention to a comparison between experimental measurements of these constants and the theoretical calculation between these of these various contributions for the Keesom, the Debye, and the London dispersion force. So you can get a sense of how much each interaction potential energy contributes for maybe a dozen or so different molecules. So you can look at this table and see how close experiment and theory are in many cases. Lastly, I think it's important to try to provide some global overview of the entire discussion that we've had during week 1 of this course. I personally think it's important for you to try to understand how these different forces arise and how big each interaction force is compared to the others. There have been explicit equations that have been derived, and that allows you to estimate the interaction potential energies for a wide variety of different ions and molecules interacting one with respect to another. This flowchart diagram just tries to summarize everything we've discussed in the previous week. In particular, I call your attention to the light orange colored box on the bottom. This summarizes the van der Waals forces that arise when atoms or molecules without permanent dipole moments interact one with respect to another. And it's these van der Waals forces that are going to contribute the dominant interaction between the tip and the substrate. So the end result of this discussion is is an appreciation of these three different forces, and we're going to now use the insights that we've gained from discussing this. We're going to use that to actually calculate the net interaction force between a tip that's suspended a distance d above a substrate. And we're going to do that calculation by summing up all the individual interactions between atoms in the tip and atoms in the substrate, sort of as I got schematically indicated in this particular slide. So when you come back for week 2 of the lecture, we'll start to perform this integration, and we'll start to get interaction forces between tips and substrates using a lot of the physics that we've discussed in this first week of the course. So stick with it, pay attention to the slides. I think it's worth your while to try to go through and understand some of what I've worked out. And we'll see you next week as we move into week 2 of the course.